Hi, this video is about the so-called dot product of two vectors. Previous videos have dealt with vector addition. Vector addition is basically where you line up a number of vectors, maybe two vectors. You put the head to the tail, to the head, to the tail, and so forth, and you see where it ends up. Vector addition is fairly straightforward and commonsensical. But there are places in physics where you want to multiply two vectors together, and it can get a little complicated. The simpler, there are basically two ways to multiply vectors. There is the scalar or dot product, which ends up, if you remember what the definition of a scalar is a scalar is a non-directional quantity. And so the scalar product of two vectors does not end up with a vector. It doesn't end up with something that has direction. It ends up with just a magnitude of these two vectors multiplied by each other. There is another kind of product of vectors, and that is a vector product, sometimes called the cross product. Now, I personally think these videos are roughly related to Young and Freedman's university physics, and this particular video is queued to the section 110. And the next video goes with cross products. I personally wonder whether it's wise to introduce vectors this early in the very first chapter, since you don't use them until later chapters in the book. You don't actually need to know how to find the dot product of something until chapter 6 in Young and Freedman, when we get to work. And similarly, you don't really need to know about the cross product until chapter 10 in Young and Freedman, when you get to torque. And so if this seems a bit difficult and you're just starting off in physics and you wonder, wow, I don't understand this, don't drop the course. Come back to this when you actually get to, say, chapter 6. So this video is about the dot product. Again, the dot product of two vectors does not end up with a vector. It ends up with a magnitude, or what's called a scalar, which is a magnitude without direction. In the previous video in this collection of videos, it talked about vector addition. And like I said, vector addition is fairly commonsensical once you kind of get your head around it. You basically put vectors arrow to tail one by one, and you see where it ends up. But there are times where you have to multiply two vectors, and that's where the dot and the cross product come in. So, the dot product. I think once you kind of understand if I can communicate the dot product, it again is not real difficult. And so, for example, work. This is from chapter 6. Work is not a direction in physics. Work is a scalar. It just is an amount of work that's been done. But you can think of work, one way of thinking of work is to think of it as the dot product of force and displacement. Let me explain. So for example, you might have a displacement in one direction. I have the D here. But the force might be going in a slightly different direction. And so the dot product basically either looks at the force times the component of the displacement going in the same direction as the force, or if you wanted, you could take the displacement and treat it as the base, and then look at the component of the force that is going in the same direction as the displacement. The bottom line is that you're multiplying the components of these two vectors that are going in the same direction. And so the dot product multiplies the quantities of two vectors in such a way that you end up with a resultant magnitude, and that multiplication is going to be the parts of the vectors that are going in the same direction. Now this involves a little trig. So for example, in this picture, the displacement is going in one direction and the force is going in a slightly different direction. But if you make a right triangle out of the displacement, and you treat this as the opposite side of some angle theta, and this as the adjacent side of some angle theta, then you remember from trigonometry, that the cosine of an angle, so for example the cosine of theta is the adjacent side right here divided by the hypotenuse right here. And so if you multiply it out, what you end up with is that this this component of the displacement that's going in the same direction as the force is the hypotenuse, d, times the cosine of theta. So the dot product multiplies the magnitude of the force times the magnitude of the displacement going in the same direction as the force. And so we say that the dot product of the force by the displacement is the quantity of the force, the magnitude of the force, times the magnitude of the displacement times the cosine of theta, where theta is the angle at which the displacement is in comparison to the force. Let that sink into. That really, once it clicks, you'll say, okay, I understand what this is doing. So the dot product is, again, the dot product of vector A dot product with B, vector B, is going to be the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle between those two vectors. Similarly, if you flip it around, and I'm sorry, I should have flipped the B and the A and done B, vector B dot product vector A. These are actually commutative. It doesn't matter which order they go in. But if you were to flip it around, that you could also say that the dot product is the magnitude of B times the magnitude of A times the cosine, and I've come up with a different angle here, angle phi, where you're treating, say in this case, where you're treating vector B as the base and phi being the angle the other way around. And so it's gonna end up being the same, because dot products are commutative. That is, the dot product of A and B, vector A and B, is the same as the dot product of vector B and A. Well, that's just a quick overview of the dot product, and I hope it's made some sense. The way I conceptualize it is the dot product is the multiplication of two magnitudes which are going in the same direction. And if the vectors aren't going in the same direction, then you have to find the component of the vectors so that they are going, the components are going in the same direction. And the way you do that is by multiplying AB times the cosine of the angle between them.